Hi everyone, in this video we're going to start chapter 15 and look at 15a, continuous random variables. This section is quite large, so I'm going to say it now, and this will probably be a two-part section. So I would encourage you to probably watch the first part, fill in the notes, and then take a break before you watch the second part because there's a lot of information to take in. So in chapter 14, we looked at discrete random variables. Here we look at continuous random variables. So the main difference between discrete and continuous, and I shouldn't say this will always be the case, but usually discrete values we can count and continuous values we measure. So, things like height and weight we can measure. So with continuous random variables, we look at values that can take on any, variables that can take on any value within a number line. I should just read what it says on the screen. So, it can be between, say, 1 and 10, and it can take any value. So it doesn't have to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So not the discrete values, but it can be like 5.1333333, something like that. All right, so there's an example there. I'm not going to cover everything because I'm sure you can read that in your own time. All right, what we have here is if we were to graph, I'm going to read that. So determine the value of this probability. You could begin by measuring the weight of a large number of randomly chosen people and determine the proportion of people in the group who have weights in this interval. Suppose after doing this, a histogram of weights was obtained. So what we have here is a histogram. You should be familiar with a histogram. So histograms look at intervals. So this highlighted part is between 82.5 and 83.5. So if we wanted to find the probability that the weight was 83, basically it's just the area of that rectangle over the total area. All right, and you can see that working out there. All right, I'm not going to spend too much time because it's such a long section. All right, so now suppose the sample size gets larger and the class interval width gets smaller. Sorry, I just need a drink. I made a cup of tea and had a sneaky biscuit, and now the sneaky biscuit is stuck in my throat, so I keep getting it stuck. All right, so now suppose the sample size gets larger and that the class interval width gets smaller. If theoretically this process is continued so that the intervals are arbitrarily small, then the histogram can be modelled by a smooth curve. Okay, so basically this means as these class intervals get smaller, your rectangles are going to basically represent quite a smooth curve, so the red line on the graph. The curve obtained here is of great importance for a continuous random variable. Okay, so this is what you need to know. All right, so the function f, whose graph models the histogram as the number of intervals is increased, is called the probability density function. The probability density function f is used to describe the probability distribution of a continuous random variable. Now, as you are aware, we've done definite integrals, okay, to find the area under the graph. So that's basically what we do for probability density functions. Okay, so you can see here the weight of 83 is within the interval 82.5 and 83.5. So we can use a definite integral to find that area. So we don't necessarily have to approximate it using the rectangle. We can use a definite integral to find the exact area. Okay, so remember back to when we did definite integrals. All right, so probability density functions, let's just go here. So in general, a probability density function is a function with domain over some interval such that f of x is greater than or equal to 0. Okay, so your function has to be greater than or equal to 0 for all x in the interval. So basically it's got to be over the x-axis. And the area under the graph of the function is equal to 1. So why do you think it's equal to 1? Because all probabilities have to add up to 1. Okay, the sum of all the probabilities have to add up to 1. So if your domain, sorry, I'm pointing with my cursor and I realize that you can't see my cursor on here. So let me just highlight. So if you're, and now I don't, oh, it's not working for me. I wonder if it works on here. No. Let me just do it like this. Okay, so if your domain, I can highlight it with, my little tablet's not working. If the domain of f is CD, okay, so what we have is the definite integral from C to D is equal to 1, okay, which is basically what we just said at point number 2. So your domain is from C to D. But in many cases, the domain of f will be unbounded such that we're going from 1 to infinity, or we're having all real values. Okay, so if that is the case, then we can use different notation. So if we're going from 1 to infinity, we can just say, all right, we're going from 1 to k, where k is approaching infinity. So we're just introducing that limit there to show that, well, we're going from 1 to k, but the value of k is approaching infinity. Then if we're going from, if the domain is any real value, we're going from negative infinity to infinity. Okay, so you can see that on your definite integral, but just like before, instead of writing your lower limit and upper limit as negative infinity to infinity, we use k. All right, and then just say on the limit as k approaches infinity. All right, so definite integrals which have one or both limits, infinite, okay, are called improper integrals. Okay, so we don't have a limit on these last ones that I highlighted with k, so they're called improper integrals. Okay, so there are possible complications with such integrals which we avoid here in methods, and you'll only need to use the methods that we look at in examples 1 and 3. Okay, so we'll look at them in this video. Actually, I wonder, did I put them on here? Let me just quickly scroll. Oh, there's example 3. Okay. So we'll get to that in a sec. Sorry. Oh, glitchy. All right, so what we have in this green box, okay, you can see we're now finding the probability density function of x between two values, a and b. Okay, so our function looks like it's going from negative infinity to infinity, but we only want to know it from a to b. So we just set up a definite integral. Okay, so if we're going from a to b, so let's say we were going from 1 to 10, a would be 1 and b would be 10. So we're just finding the area under that curve will give us that probability. So there's a lot of information here, but it's not as complicated as you might think, because you've learnt about definite integrals and now we're just applying it to probability. Okay, so we have a probability density function, so that red curve, and we use this for continuous data or continuous random variables. And all we need to do to find the probability is to find the area under the curve. What we have here is it doesn't matter what inequality sign you have, they all mean the same thing. So if we've got x is between a and b, but not including, they're all the same. Okay, it doesn't matter which inequality sign you use, they're all the same. Okay, so you don't have, it's different to discrete random variables. Remember, if you wanted to do less than 7, then 7 wasn't included. But here, because it's continuous data, it doesn't matter with your lower limit and your upper limit and the inequality sign. All right, so that's that green box at the bottom, just summarizing what we've already said. So f of x is greater than 0, and your probability, or your probabilities added together have to equal 1. All right, so let's look at it. My screen goes glitchy. Let's look at a few questions together, and I might stop at about 30 minutes. So we'll see how many we get done in 30 minutes. All right, so example 2. Question 2, let x be a continuous random variable with the following probability density function. Okay, so it's written as a hybrid function. So that just means we've got a hybrid function just means, oh, my pen. Sorry, I just had to unplug my tablet and plug it back in. Okay, so just means we've got multiple functions. So well, I can highlight that anyway. So we have x squared plus kx plus 1 when x is between 0 and 2, and f of x is equal to 0 everywhere else. So if we know it's a a continuous random variable, when you see that term, you're thinking of definite integrals. So I'm going to set up my definite integral, okay, and we're going from 0 to 2, and this is not very nice too. And your function is x squared plus kx plus 1. And we know that all probability density functions have to add up to 1. So that's equal to 1. The 0 is, irrelevant in this case. So we know that x squared plus kx plus 1 is the only function we're going to be looking at. All right, so then we just treat it like any other definite integral. So I'm going to do it by hand, but obviously you can also solve it on your calculator. All right, so the antiderivative of x squared is x cubed over 3. The antiderivative of kx is kx squared over 2, and then 1 becomes x. And then we're going from 2, 0 equals 1. All right, and then we just solve for k. So we've got to substitute in 2. So 2 cubed over 3 plus 2 squared times k over 2 plus 2. And then when I substitute in 0, I'm just going to get 0. So we can just say that is equal to 1. And then we can just solve all that, which is a bit annoying. So I'm just going to do it on my calculator. All right. So if you were doing a question like this on an exam or on your SAC, you would probably get to this point and then just, if you had your calculator, you can just do it on your calculator. This isn't that hard to do, but because it's very early in the morning, getting this done before your lesson. So probably better to do it on the calculator just in case I make a mistake. I'm going to use x instead of k just because I can't be bothered going to the keyboard. But just make sure if you do what I just did and use x instead of k, just make sure you write your answer as k. Oops, we've got to make that equal 1. Comma. Oops. I'm using my little stylus to press them and sometimes it doesn't work. Okay. All right, so we've got k. Now we've got to see what form the answer has to be in. Okay, so it doesn't say as decimals, so I do have to go back and put my answer as a exact value. All right, so negative 11 on 6. All right, moving on to question 3. So consider the random variable x having the probability density function with a rule. Okay, kind of same situation as before. Question A, sketch the graph. Okay, so we're going to have to sketch 12x squared times 1 minus x, and then we're going to find the probability and shade the region which represents this. So we're going to use our calculator. So I haven't done this yet on my calculator, but it's not a hard one, so hopefully we're able to do it. So 12x squared, and then 1 minus x. Okay, and put your limit in. All right, so we just want to go from 0 to 1. The reason for that is because this is a cubic and you only want to see it from 0 to 1. So go to keyboard. All right, and we're going from 0 to 1. Should just use my keyboard. All right, and then we'll tick it and we'll graph it. Now, if you can't see it, which is a bit weird there, let's just go to zoom, or not, is it auto? All right, so I might actually, just because it's stopped there, 12x squared, just make sure I've put it in correctly, 1 minus x, and we're going from 0 to 1. All right, I was just playing around with the zoom to see it a little bit better. So when you do your graphs, I would play around with these. Yeah, because auto won't always give us what we want. So you can use the box to just highlight what section you want, although when I was doing that, it wasn't really working too well for me. But just playing around with the window so you can see it a little bit better, because the end point should go at 1 and before it looked like it didn't go to 1. All right, so there's our graph. If we wanted to sketch that from the calculator, the important parts would be looking for the maximum. Okay, so if we go to max, it tells us there, so you can see that the maximum point is at x equals, that's 2/3, and you can get the if you want the exact value, you can just substitute it into here, or use the main screen to find that maximum value. But when you're sketching, you should really put in your x-intercepts and the maximum value. All right, so there's our graph. I'm going to just quickly put it on the screen. And I know it's going to disappear as soon as I click. Okay. All right, let me get it back up. So it's not symmetrical, so it's not like a parabola. Remember, it's a cubic, so kind of want to make it. Let's try it in red. Okay, so we're going from 0 to 1, and this point here, your maximum, what's that at? 2/3. And I just know that because it's 0.6666. And then we've got 1.77777. So that is 1 7/9, I think. But we can just substitute it into here, but just because we just don't have time at the moment, I'm just going to leave it as a decimal value. Okay, so there's our graph. Very rough sketch. For part B, find the probability that x is less than 0.5. So we can easily do that on the calculator screen. Let me just get my calculator back up. All right, so we want to do integral and all right, the graphing screen is not working for me at the moment, so I'm just going to do it the other way, which I prefer. So we're setting up a definite integral. All right, but going from x is less than 0.5, so our lower limit is 0 and we're going up to 0.5. And then our function is 12x squared 1 minus x dx. Oh, I think I may have forgotten dx up here. All right, never forget your dx, sorry. I'm going to put that on. Okay. And now we just solve that. So If you expand, this is an easy expansion, so probably easier to deal with the expanded version. So 12x squared minus 12x cubed. And then you can just do that by hand quite easily. I'm just going to do it on the calculator. Not that calculator. Sorry. All right, let's go to the main. All right, definite integrals. All right, so we've got 12x squared minus 12x cubed, and our lower limit is 0, upper limit is 0.5. All right, and just make sure it's all written there. Okay, so it's 5/16. Now, part C, it says shade the region which represents. Okay, so if I know that the turning point is at 2/3, so a half is less than 2/3, I'm just going to put that here, or halfway between 0 and 1 anyway. So there's 0.5. And I'm sorry, I just couldn't get the calculator doing this. So there's the shaded region that we just found. All right, let's move on. So what we're going to look at here is an unbounded domain. So in the previous two questions we did, we had the domain was bounded. Okay, so in the previous one we were going from 0 to 1, and the one before that was 0 to 2. Okay, but here it's not bounded. So we're either going from negative infinity to a value, or a value to infinity, or negative infinity to infinity. And you can see we're introducing the limits. What the limits just mean is as k approaches infinity, or as k approaches negative infinity, because infinity in itself is not a point, not a value, okay, because it goes on forever, numbers go on forever, so to imply that we use infinity. Okay, so example number 3. Now example 3 is done on video in your textbook, so I'm going to get the lovely lady to talk you through it, because sometimes it's just a little bit easier to get someone to...
The first part of this example asks
us to sketch the graph of f. So there you can see I've set up my axes and I've got a decreasing exponential function, but we're only following this exponential function when x is greater than 0. So I've put in an open circle endpoint at x equals 0, and I've erased the rest of that graph that was continuing up there. The other piece of information in this hybrid is that we follow f of x equals 0 for x is less than 0. So that means I need to have a nice thick horizontal line there at y is equal to 0. I've also included down the bottom here our asymptote to show that this graph here is approaching y equals 0. To finish it off, I've labelled my axes. Part B asks us to show that this is a probability density function. So in doing so, what we need to show is that if we integrate this function between negative infinity and positive infinity, the value of this area will be 1. But I don't need to integrate between negative infinity and positive infinity. We can see from our graph that we only need to integrate between x equals 0 and positive infinity. Now the thing is, we can't actually integrate all the way up to infinity without the use of a limit. So what we're going to do is call this number k, and then out the front we're going to say as k approaches infinity. When I integrate this expression here, it becomes 1 over negative 2 out the front multiplied by 2e to the negative 2x. And again, we're going to integrate this between 0 and k, where k is the number that approaches infinity. When I tidy that one up and then substitute in k and substitute in 0, I end up with this expression here. Now this is where the limit comes in. We have to ask ourselves, what happens to this term here as k gets bigger and bigger and bigger? This denominator gets bigger and bigger and bigger, in fact, very, very quickly. So if we've got 1 divided by a very, very big number, this in effect becomes very, very close to 0. So this whole expression here ends up becoming 1 plus a tiny, tiny, tiny little number, which is so insignificant we choose to ignore it. So therefore, the value of this limit is equal to 1. Part C asks us to find the probability that x is greater than 1. So graphically, what we're doing is setting up an x value of 1, and we're looking at the area from there onwards. So using integration, what we're going to do is evaluate the definite integral of this function between 1 and infinity. Now, just like before, we cannot technically integrate between 1 and infinity. What we need to do is introduce the variable k, where k is a number that's approaching infinity. So we know from part B that the integral is equal to negative e to the negative 2x. Then we're going to substitute in k into this expression and substitute 1 into that expression. And again, we're going to ask ourselves, what happens to this term here as k approaches infinity? Now, just as before, this becomes a really, really tiny number that is practically insignificant. So the value of this limit becomes e to the negative 2 plus this tiny, tiny, tiny little number, which we end up ignoring. And so we say that the value of the limit is e to the negative 2, which can be written as 1 over e squared.
Awesome. Okay, let's go back to our notes. So you can also see the example there. Okay, but I think that video kind of explains how limits work, which is very important to understand. All right, here we've got some calculator instructions. So you can see they've set up the hybrid function, so f of x. Okay, so defining f of x and graphing it. And instead of writing everything each time, just putting in f of x. So this is the same question as before. Okay, so this example here, it's just done on the calculator. So defining it just means that when you graph it, you can see, as the lady said in the video, that's the region we just realized that you can't see my cursor. So she graphed this. Okay, so remember, but also this part here, which I didn't do in the previous question that I did with you guys. All right, we might just stop with question 4 in this video. So we'll do this one together. So consider the random variable y with a probability density function f of y equals blah, blah, blah. Find the constant k and find the probability that y is greater than or equal to 2. All right, let me just write part A. Okay, so when we're looking at this hybrid function, we're really only looking at the first function because we don't need to look at when y is less than 0. This one here, they've defined the probability density function as y, but we tend to use x. So don't let that confuse you. So if we were to do a definite integral, okay, we're just going from y is greater than 0. So we're going from 0 to infinity, and our function is k e negative y, and that's with respect to y, so dy. Now remember from the video, we have to introduce a limit when we're working with infinity. So I'm going to introduce the limit. So as k approaches infinity, okay, so instead of having infinity as my upper limit, I'm going to use k. Oh, all right. The problem with that is we've already got a k in the question, so I'm going to use a different letter, which is a bit annoying. I'll use what the textbook uses, a. All right, so don't go using a different question, sorry, a different variable if it's already used in the question. And I've got a staff meeting in 7 minutes. So I might get heaps of things popping up in a sec. All right, so let's be quick. All right, so as a approaches infinity, and there's our function. So we need to find the antiderivative of that. So we're going to have to take that coefficient of y out the front, so negative k e negative y, and we're going from 0 to a. All right, just had to pause to attend a meeting, so let's get back to it. So we're substituting in, get my pen ready, a, so negative ke to the negative a minus negative ke to the negative 0, and that is equal to 1. So we've got negative ke to the negative a, then we've got two negatives, so it's going to be plus, and then anything to the power of 0 is just 1, so it's plus k equals 1. And silly me, I keep forgetting we should be writing the limit on as well. Look what happens when you rush. Okay, and then now as a approaches 0, so if you wanted to think of this as negative k over e to the power of a, so as this gets, no matter what k is equal to, as a approaches infinity, as we saw in the video, it becomes really, really big. And any number over an extremely large number is going to be very insignificant. Okay, so we're going to have plus k equals 1. So effectively, as a approaches 0, this part here is really small. Okay, so we don't need to count that. So we just say k is equal to 1. All right, let's quickly do b. Do I have space down here? I do. All right, so in part B, we're finding the probability that y is less than or equal to 2. So less than, so 2 is going to be our upper limit. And we now know k is equal to 1. So I don't need to write it in terms of k, so I can just write e to the negative y dy and just solve that. So the definite integral is going to be negative e to negative y from 2, 0, and just substitute in 2 and then substitute in 0. All right, so we've got negative e negative 2, sorry, a bit wonky there, and anything to the power of 0 is 1, so we're going to have plus 1. And I should just tidy that up. We're going to have 1 minus 1 on e squared, or you can leave it as a negative integer, a negative power if you like. All right, so obviously you can also do it on your calculator, but ones like this are very easy to do. Don't let the e scare you off. All right, I'm going to leave the video there. Make sure you watch part 2 when it's ready. All right, bye guys.